Many data engineers are waking up to a terrifying headline. They see AI writing SQL, generating ETL scripts, and cleaning datasets automatically. The fear is immediate: if code generation is automated, isn't my entire career obsolete overnight? That anxiety is understandable, but it rests on a fundamental misunderstanding of what actually powers the artificial intelligence revolution. While models can generate syntax, they cannot architect the physical infrastructure required to run that syntax efficiently. As long as GPUs and TPUs require human-designed data pipelines for memory bandwidth optimization and interconnect efficiency, data engineers are not just safe, they have become more critical than ever before. The core of this fear loop is confusing code generation with system reliability. When you watch an AI write a query in seconds, it feels like the hard work is gone. But that generated code has to run somewhere. It needs to move terabytes of data across networks and fit into finite memory pools on expensive silicon chips without crashing. This is where the hardware reality contradicts the hype. Current analysis from Gartner confirms that while AI can generate snippets, it cannot physically build or maintain the massive infrastructure needed for training and inference. The physical constraints of silicon mean that autonomous agents lack the agency to design efficient data pipelines because they do not understand the trade-offs between time and space on a specific processor architecture. Consider the bottleneck that defines modern AI: data movement. In high-performance computing, moving data from memory to compute units is often more expensive than the computation itself. If your pipeline moves data inefficiently, you are burning millions of dollars in cloud costs for nothing. An LLM might write code that works on a small dataset but fails catastrophically when scaled because it does not account for cache locality or network latency constraints. It cannot guess its way out of these physical limits without human oversight. The engineer's value has shifted from writing syntax to orchestrating complex systems under real-world hardware constraints, ensuring that the data flows as efficiently as possible through heterogeneous clusters. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This necessity for human judgment becomes even more apparent when we look at reliability in distributed environments. Training large models involves hundreds or thousands of nodes working together. In these high-stakes settings, you must tolerate up to 1/4 of your worker nodes failing or acting maliciously without the entire training run crashing. This is known as Byzantine resilience. Current research shows that while algorithms can handle this level of failure, they require human-designed outlier filtering procedures and gradient compression strategies that adapt specifically to non-standard data distributions. Let's look at the specific mechanics here. In these systems, we use techniques where communication bits are reduced by a factor of d divided by k, meaning for every dimensionality d in your model, you only send k coordinates across the network. This reduction is vital because it prevents the system from choking on data traffic during training. However, implementing this compression effectively requires understanding exactly how your specific hardware topology handles partial updates and where to place filters to catch bad gradients before they corrupt the global model state. An autonomous agent cannot autonomously guarantee these robustness guarantees in production environments with non-standard data distributions because it lacks a physical body or direct access to silicon constraints. It simply does not know which node is acting maliciously versus being slow due to network jitter without human-designed logic guiding its interpretation of system signals. This brings us to the gap between what AI tools promise and where they actually land in enterprise settings. There is a growing class of AI data scientists or autonomous agents that can handle 40 to 50% of routine cleaning tasks. They are impressive for simple workflows, but when you look at real-world adoption, 71% of enterprises use 4 or more fragmented tools to manage their data stacks. The failure rate in these initiatives delivering actual value is estimated between 80 and 85% because the AI cannot stitch together these disparate systems into a cohesive whole. The human role has evolved from being a data wrangler who writes endless scripts to becoming an infrastructure architect. You are no longer just competing on how fast you can write SQL. You are competing by designing the architecture that allows those queries to run efficiently on expensive hardware. The job is shifting towards understanding the trade-offs between memory bandwidth limits and compute throughput, structuring data so it moves seamlessly through heterogeneous clusters without creating bottlenecks. This requires a level of judgment about system behavior under load that AI currently cannot replicate because it lacks the context of physical reality. We are seeing a fundamental shift in computer science where routine syntax is automated, but the maintenance of large-scale systems remains a deeply human task. Software engineering is fundamentally about maintaining reliability and ensuring complex interactions work together over time, tasks where current AI still struggles to provide consistent guarantees without human intervention. Think of civil engineers who do not weld every single beam themselves, but design the load-bearing logic that ensures the bridge stands firm under stress. Data engineers are now doing exactly this for the digital infrastructure that powers AI, designing the pipelines that allow models to learn and infer at scale. The future is not about humans being replaced by machines. It is about humans managing the physical reality of silicon while AI handles the repetitive syntax. As adoption grows, the demand for engineers who can manage these complex systems will increase rather than decrease. The AI data scientist tools are powerful assistants, but they rely on human-engineered pipelines to function without catastrophic failure in production environments. Your career is not ending, it is maturing into a role that manages the very foundation of the AI revolution. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.